Hello, hello. Okay, so we were discussing about this randomized mean card. Okay, and in this case, we have seen. Okay, we are choosing the edges randomly. Okay, and we have seen that in two of the implementations we have seen, and we have seen that okay, in one of the cases we are getting the min card. Don't talk. Okay, in one of the cases we are getting the min card, and in another case we are not. Hello, you, no, you come here. You come here. Are you spread apart? Go there. Ah, first you sit. Then you sit there. Then you sit there. Hmm. So, in one of the cases, we have seen that we are getting the min card, and in another implementation, whenever we are choosing edges, we are seeing that we are not getting the min card. Okay. That we have seen so far, and we have argued that okay, uh, in these cases, we are getting that okay, the randomized implementation is not giving the correct answer. Then we raise the question: then what is the utility of using this randomized algorithm? Okay. Whenever at some point of time, or in some cases, we are not getting the proper result. But the thing is that this thing, we are not getting the good result, is having, we have to prove that is having very less probability. Okay. That means with more than 99% chance that we are getting the min card. Okay. So if that is if we can make the randomized algorithm is behaving like that way, then we are done. Okay. So in this parlance, we have discussed two types of randomized algorithm: Las Vegas and Monte Carlo. Right. Now this analysis we have to do. Okay. So this Kargar's min cut algorithm. Kargar's min cut algorithm, we have to do the analysis. And we have to ultimately prove that okay, it is greater equals to 99% that we will be getting the min cut with this type of implementation. Maybe we have to modify the algorithm, that preliminary algorithm a bit. Okay, that modification we will see also. Right. So let us start this analysis. So first we have to observe that we are in this randomized min cut algorithm, we are picking the edge randomly. Okay. Right. And then we are contracting and making the super node and proceed. Okay. So the whole idea is we are choosing the edges randomly. Right. Like the quicksort implementation of randomized version, we are seeing that okay, we are choosing the pivot randomly. Okay. Right. You come that side. You come that side. You shift a bit here. In my purview, come. Now the question is when the algorithm will return the min cut. Okay, right? Say this min cut is in this example is B. Okay, when it will return, we can say that whenever I am picking edges, okay, that until and unless we are getting two nodes surviving, we are picking edges randomly. Okay, so in that case, so two edges whenever we are having, two nodes we are having, we are picking edges on and on. So in in those iterations, whatever we are having, okay. So in those iterations, if B and D are not selected, as the as the edges whenever we are picking, then B and D will survive, and then we will be getting that B and D will be the min cut. Okay. So when this algorithm will be returning min cut, when the min cut edges are not selected in iterations. That is the first simple observation. Okay, definitely, right? So that means B and D survives in all iterations. If B and D survives, that means not picked up whenever we are picking it randomly. If B and D survives in all iteration, that is they are not picked up in the age contraction procedure, then we can say that B and D will be the min cut. Okay. So that means okay. So we have already said that this will be happening with high probability. Now another thing is that we have a min cut, for example, B and D, and then this min cut consisting of k edges. Okay. So whatever graph we can perceive, okay, that graph will be having a min cut, right? And that min cut will be having definitely some k edges, right? This graph, in this graph, we are having k equal to 2 edges. That is the min cut, B and D maybe, or AD. Okay, that could be the min cut, right? So k will be equals to 2 in this example, in our example graph. If I am having the the graph might be complicated enough like this, okay, then we can have okay, maybe k equal to 3. Okay, so as the graph will be changing, this k will no longer be only 2. Okay, it may be 3, it may be 4, whatever, right? But in our example graph, it is k equals to 2. That is another observation. That means the min cut will be having k edges. Min cut will be having k edges. With that, we will be proceeding because we will no longer be we perceive the idea with this example graph. Now we will be generalizing it. Okay, we will be thinking that any graph is presented and we are finding the min cut. So that min cut will be having k edges. In our example, it is k equal to 2. Okay. Now what we are trying to estimate is that in this graph, how many edges might be there at least. Okay, we are approximating that way, right? So for this, say now consider a cart. Now consider a cart which will be putting a single node in one side and remaining n minus 1 nodes in another side. So what I am telling that consider a node, okay? So this node I am considering in this example graph, this node, and I am separating the graph like this way that okay, this node will be in one portion and the rest of the graph will be in another portion. Okay, so that is a cart, right? Definitely. we can have a cut here, we can have a cut here, we can have a cut here. Okay. So this thing we are doing. Okay. We are putting, we are considering a cart which will be putting a single node in one side and the remaining n minus 1 nodes in another side. Okay. So you see, putting one node in another one side. So if this guy, you see this guy having some incident edges on it. Okay. Whenever I'm having a cut like this, so all these incident edges will be considered. And what all these incident edges, the meaning of all these incident edges in parlance of a node in the graph, meaning what? What? So the meaning of this graph, the meaning of these edges in this node is called its degree. Okay. So the number of edges incident on this node. Okay. The definition is that it is the degree of this node. Okay. So in our example, this card will be containing the node 3 and rest of the nodes 0, 1, 2 will be in another portion. Okay. This card consisting of 3 edges, DCE, DCE. Okay. So these 3. So it is D, this is C, and this is E. Okay. This is a valid card. This is a valid card, but may not be the minimum card. Maybe or may not be, right? So it can be bigger than the minimum card, right? So it may be the min card or may not be. So if I am having a cut here corresponding to these 2, that is the minimum cut we can have, right? So from this observation, what we can say? What we can say, a closer look at this card DCE reveals that DCE is the degree of any arbitrary vertex 3, and we have seen that this degree, that means this card consisting of these edges, may not be the mean card, maybe bigger than that. Okay. So what we can say that all vertices in the graph, but we know that the mean card in this graph is having k edges equal to 2. The number of edges of the mean card in this graph is 2. But if I am considering this card and the degree of this, that means this card consisting of more than 2 edges. Okay. So what we can infer? That means the degree of each vertex in the graph must have degree k or larger. Okay. So you see in this graph, this node, then you see the degree of this node is 2 and the min cut is 2. So the degree of this node is 3, but the min cut is 2. Degree of this node is 2 and the min cut is 2. So all vertices in the graph must have degree k or larger. Okay. So this is the biggest observation of proving this thing. Okay. The further proceeding, this observation is a killer observation. Okay. So we can say that degree of each vertex in the graph, is at least k, right? The degree of each vertex of the graph is at least k, maybe more, right? What is this k? What is this k? K is the mean cut. That you have to always remember. In other words, that In other words, each vertex is adjacent to at least k edges, that is their degree. So that observation we have already said. Now, what we are doing, we are having in this graph, we are having 4 nodes in our example graph. Okay. And if I am thinking that, okay, this node having degree k equal to 2, right? So this node having degree k at least, the word should be, so it is, we should be using the word at least. Okay. So if I am thinking that, okay, let us suppose that each node in the graph having degree k, okay, right? So in this case, how many edges of the graph we will be having? Okay, how many edges? So if I am having these nodes, so each node will be having degree k. That means what? Each node having two number of, say in our example graph, two number of incident edges. Okay, two number of incident edges. How many such nodes we are having? N number of nodes. So how many edges will be having? Nk. But why it is 2 divided by 2? We should be having 2. Huh? So whenever I am considering this edge, right? So this is incident on this node as well as this node. Okay. So it is double counted. Each edge is double counted whenever we are considering the number of edges in the graph, right? So that's why this is the number of edges of each node, means the number of incident edges, but that should be divided by 2 because it is double counted for each node. Okay. So these will be the at least these many edges must be there in the graph. These many edges must be there in the graph. Okay. This is the at least these many number of edges must be there in the graph. So this is the first mathematical inference we have got from this. Okay. Right. Now, now let us see when the first stage is contracted. Okay. So first stage I am picking up randomly. Okay. So the first contracted edge is chosen uniformly at random from the set of all edges. Okay. From the set of all edges. So we have got that the number of edges in the graph is at least nk by 2. Okay. So these are the set of edges we are thinking right now the graph is having. Okay. And from this set of edges, we are picking up one edge randomly. Okay. Right. Since there are at least nk by 2 edges in the graph, at least, and the min cut has k edges. Min cut has k edges. Okay. So the probability that we choose any one of these k min cut edge is, it should be at most. Is at most. That means we are having nk by 2 edges in the graph. And we know that k edges are the min cut. Okay. So we are trying to see the probability that whenever I am picking one edge, that will be from one of the k edges, that is the min cut. Okay. So what is the probability of that? So we are having favorable case k. Out of this k, that means in our example graph, that could be say b and d. So this b and d. So either b could be selected or e could be selected. Okay. Right. Okay. So these favorable cases is k. K is the min cut. Okay. So if I am picking up the first iteration, any one of these B and D, then we will not be getting the min cut. Okay. So we are seeing that what is the probability that we can choose either B and D, B or E. Okay. So you are having favorable cases K, K favorable cases, K is the min cut. And how many edges we are having in the graph? Nk by 2. So this is the probability that any of the K edges which could eventually be the min cut could be selected in the first iteration. Okay. Are you with me? Huh? Okay. So why I am calling that this is the at most, the probability that we are choosing it at most. Okay. So you see we are going with the graph is having at least these many edges, at least. Okay. So look at this. If I am having 1, say 1 by 2, what is the value? If I am having say 1 by 4, huh? Sorry? 0.25. Right. So you see these two, the denominator, if I am increasing, keeping this remaining the same, keeping this remaining the same, keeping this same, then what will be happening? We will be having the value less. Okay. So nk by 2 is the minimum number of edges the graph could have. Okay. But in the original graph, we might be having more edges. Okay. It might be having exactly nk by 2 edges, or it could be more, right? So it could have 2 edges, or it could have more than 2 edges. So keeping this same, say k equals to 1. Okay. 1 is the min cut. In our first example graph, the min cut was 1. Okay. So if k remaining the same, then if this is increasing, right, so then the probability will be decreasing. So whenever I am dividing nk by 2, whenever I am dividing k by nk by 2, then that is the at most probability. At most this much is the probability. If I am increasing the number of edges in the graph, that is the possible case. Okay. Then we are having the probability will be decreased. So we can say that whenever I am in the first iteration, I am selecting one of the k edges. Will be having the probability at most this. So k by nk by 2 means it is 2 by n. Okay, so this 2 will be here, k will be cancelled out, then it is 2 by n. Okay, so this is the first, this is one in the first iteration what will happen. Okay. Now let us see that okay, this is out of these k edges, one of the edges will be selected. And now what is our objective? Our objective is that the min cut will survive. Okay. That means out of the k edges, none of the edges will be selected in the first iteration whenever I am choosing it randomly. So what will be the probability of that? So this is less equal to this, then this will be greater equals to 1 by, 1 minus 2 by n. Okay. Right. So that is what it is written, that the probability that the first contracted edge is not from the k edges. That will be having the probability greater equals to this. Okay. Right. So this is for the first iteration what we have got. Right. Let us see another iteration what is happening. Okay. So in the first iteration, all k edges of the min cut survives is having the probability greater equals to 1 minus 2 by n. That we have got. Now In the second iteration similar calculation we can have. Given the fact that the first contraction did not eliminate an edge of the mean card. So given the fact that the first iteration didn't eliminate any of the k edges, which is eventually will be survived, okay, then we can say we have got the mean card. Okay. So the first iteration, no edge from the k mean cut edges is selected. Okay. Given this fact, what is the probability that in the second iteration, no edges from the k edges will be selected? Okay. No edge from these k edges will be selected. So the similar calculation we have to do. After the first iteration, we are left with how many nodes? How many nodes we are having? N minus 1 nodes, right? So 2 nodes will be contracted to 1, others remaining the same. Okay. So we had 4 nodes. In the next iteration, we had 3 nodes. Okay. Right? So now we will be thinking we are having N minus 1 nodes, right? And all the edges which are there is there. Okay. And what we have got? We have got that in the first iteration, no edge from the k edge is selected. Okay. That means all those k edges are still there in this n minus 1 nodes, n minus 1 node graph, right? So again, we will be forgetting what happened in the first. We are having n minus 1 node graph, right? And again, we will be approximating the degree of each vertex, okay, and then out of these k edges, no edge will be selected. That we will be doing. So what we can have say this probability that the second edge not from the mean card. That means second edge means in the second iteration whichever edge I am selecting. Okay. Given that the first edge was not from the mean cut, that means all the mean cut is already remaining in this n minus 1 node graph. Okay. So in the first case we have got this is greater equals to 1 minus k by nk by 2. Okay. So that means 2 by n. So this is the 2 by n. Okay. Right. So now only thing is that everything will be remaining same. The number of nodes will be only decreased by 1. Okay. So it will be greater equals to 1 minus k by k times n minus 1. These many nodes will be there in the graph divided by 2. Right. So k times n minus 1 divided by 2, that will be the approximated number of edges in the graph. Okay. And k by that is that any of the k edges will be selected, and then 1 minus that will be none of the edges will be selected in the second iteration also. So this is becoming 1 minus 2 by n minus 1. K will be cancelled out, right? Are you with me? Yes. So the first iteration what we have got, the second iteration we have got, these two observations will be leading us to formalize this statement more formally. Okay. So let us formalize this in much more rigorous mathematical terms. So let Zi or Zi be the event that the edge contracted in iteration I is not from the mean card. Okay. So what we are looking for that in any of the ith iteration, the edges I am selecting will not be from the min card. Okay. Why I am doing? Because if it is not from the min card, then we will be eventually getting the min card. Okay. Otherwise, there is no possibility of getting the min card, right? So the iteration, the first iteration, the second iteration. So we can say that so this xi be the event that is the intersection of the events that j equals to 1 to this I up till I. So this zj be the event that no edge of min cut was contracted in the first I iterations. Okay. So in this is that means it is z1. So intersection z2, intersection up to zi. So this term, that means zi is the z1 is the event that in the first iteration it was not selected from the min card. Z2 is the iteration, the Z2 is the event that in the second iteration that happened. Okay. And Z1 intersection Z2, that means in both the iteration, no edge from the min cut was contracted. So if I am performing up till I iteration, I could be n also. So I iteration up till that, set n I equal to 10. That means 1 to 10, all these iterations, no edge from the min card, that is the k, selected in this process. Okay, that means it is still surviving. So that is the way we can write this. And now we have to analyze this thing. So this thing we can write in a shortcut manner like this. Okay? J equal to 1 to I, Z, J. So, so this for the second iteration, by following that notation, okay, what will be the probability? What will be the probability that it is Z2 given the fact that X1 happened? That means the first iteration, no edge was selected from the K edges. Okay. So given this fact, what is the probability that in the next iteration, the k edges, none of the k edges will be selected. Okay. So that probability also already we have got. Okay. 1 minus 2 by n minus 1. Okay. Now we can write it to have much more rigorous formula. We can write that this is n minus 2 plus 1. Okay. So n minus 2 plus 1 means n minus 1. So n minus 1 is written like this because this is the second iteration. So we'll be making it much more general in ith iteration. Okay. So it might be n minus I plus 1. Okay. So that's why it is written like this. So now what we can say by following this observation, we can say that probability that it is Zi, that means given the fact that first I minus 1, first I minus 1 iterations, none of the edges was selected from these k edges. Given that fact, that means still the min cut surviving. Okay, x I minus 1 is the event that up till I minus 1 that we have defined here. That we have defined here. Xi minus 1 is the event that none of the edges from the min cut selected up till I minus 1th iterations. Given this fact, what is the probability that in the next iteration, this Zi, that ith iteration, in ith iteration also those k edges will be surviving. Okay. So that is by following this thing. So it is 2. The second iteration, if it is I, this will be I. So that means greater equals to 1 minus 2 by n minus I plus 1. So this is 1 minus 2 by n minus I plus 1. Okay. Right. Now what we got to do is, so after this n minus 2 iterations, so each iteration will definitely be contracting one node. Okay. So after n minus 2 iteration, the algorithm returns a graph with two vertices. Okay. So by definition, what we got to find out, that what is probability x I minus 2. That means up till I minus 2, all the k edges are surviving. Okay. So then that we can write probability x I minus 2 is equal to probability this first stage of the min cut, times the probability that second edge not from the min cut given the first stage not from the min cut, and so on. Okay. Right. So if this is the probability xi minus 2, so that will be z1 intersection z2 and so on. Okay. So if the probability, say these two events x1 intersection x2, if these two events are independent event, then we can say that the probability of this is x1 times probability of x2. Okay. Yes. So this is I equals to n. Yes. I equals to n here. So this is probability, good observation. Probability x1 intersection x2. So this will be the case. And here I am picking the edges randomly. So each event is independent, right? So that's why we can write that probability that first edge is not from the min cut times the probability. So this is z1, this is z2 given this x1 and so on, right? And whatever values we have got, that we have put here. Okay. So the first stage not from the min cut, that we have got 1 minus 2 by n. The second one is 1 minus 2 by n minus 1. The next one will be 1 minus 2 by n minus 2. So up till this, it will be going on, and then I have written some last terms. Okay. Some of the last terms that will be coming into picture, 1 minus 2 by n minus 5 plus 1, then n minus 4 plus 1, and so on, like this. Okay. So now if I simplify this, then it is n minus 1 minus 2 by n, that means n minus 2 by n. So like that way we have written. Okay. N minus 2 by n, then it is n minus 3 by n minus 1. Okay. Are you with me? This thing. And now you observe that, okay, these terms we have written. Little bit we can zoom in. Okay. So you see this 3 is here, and this 3 is getting cancelled out here. Okay. And this 4 is here, this 4, one term after this 4 will be cancelled out. Okay. So like this way all these terms will be cancelled. This n minus 2 will be cancelled out with this. This n minus 3 will be cancelled out from somewhere like this. Okay. This n minus 4 will be cancelled out from somewhere here. Okay. So what are the things which is surviving? So this 2 is surviving. So that is there, and this n and n minus 1. So this will be the probability. That means this is greater equals to this. Okay. probability that this x n minus 2 is greater or equals to this. Now we have got this. Okay, so this time it is corrected as you pointed out, x n minus 2, isn't it? So this 2 by n into n minus what? 1. Okay. So now you see, if I am having 10 node graph, right? N is what? N is the number of nodes in the graph. So if I put that 10 node graph, so it is becoming what? 2 by 90. Say it is almost 2 by say 100. So it is almost equal to 0.02. 0.02, what is the percentage? 2% chance. So as I told you that, okay, so if I'm randomly picking up, but the thing is that it is greater equals to, okay. So greater equals to 2% chance. Means if I'm taking, in the worst case, it will be having only 2% chance that all those cages will be surviving. And it is quite natural that all those cages will be surviving. Okay, right. So then, if I am having this algorithm, it is a disaster. Okay, we should not be using this, right? You will be arguing, no, it is absolutely not possible to utilize your ideas. That means the randomized algorithm is a bogus one. Okay. Right. So now, what is the way out? And the way out that Kargar put in this in the paper, okay. So that is we are utilizing in an ad hoc basis several times in many randomized algorithms. Okay. So is there any hope to get a good result with high probability? That is the question. And then the answer is yes, we can have. So the thing is that we have to repeat the min cut algorithm and output the min cut of all runs. Okay. So in one case, so we are repeating the min cut algorithm. So first I have returned, first I have run the that Kargar's min cut algorithm. And then I have got, okay, the min cut is 3. The next, maybe min cut is 4. Say. Next iteration, the min cut is returning 2. And then what I am telling, the min cut will be the minimum of all this. That means 2. Right. So in our example, so if I run the algorithm, the min cut several times, then we will be getting the min cut like this, the min cut value. Sometimes it is ACE, that is 3. Sometimes it is BE, that is 2. Sometimes it is ABCD, that is 4. Right. So out of this, I will be returning the minimum of all these. So that is 2. And then we are intuitively getting the result that, okay, this is the min cut. Are you getting? Then the next question is coming that how many iterations should I have? Should I have infinite number of iterations? Then there is no validity. Okay. Or can I restrict the number of iterations? Okay. So let us analyze that for this min cut, Kargar's min cut algorithm, what could be the number of iterations necessary? Right. Okay, so this little bit 10 minutes discussion we are keeping for the next class, and from the next class we'll be either we'll be having this graph algorithm or approximation algorithm.